Hello everyone, this video is about the complete machine learning workflow for classification problems. Specifically, we'll consider the end-to-end procedures for solving or training a machine learning classification model, starting from loading and inspecting a dataset, pre-processing the dataset, and then training several candidate models that are applicable for classification problems. And after training several candidate models, we will select one of the model as the best. Using that best model, we'll try to identify the relative contribution of the different input features. So we'll consider that of feature importance, and specifically we'll look at how to identify the relative contribution of the factors included in the model, specifically for linear models, tree-based models, and for those machine learning models without direct feature importance attributes. So in this data we are going to consider, or in this demonstration we are going to utilize a data related to diabetes, and our main outcome variable is diabetes. That indicates whether a patient is diabetic or non-diabetic. And there are also additional variables that can be considered as covariates. We have residence, age, height, and so on. Something like up to time ppn, or time since previous meal, or glucose load. So we are going to load this data and try to illustrate several classification models. So as usual, let's import these pandas and numpy libraries. Then let's load the data. This link will help us to load the data that we are going to use for today's demonstration. So if I run it now, the data is successfully loaded to memory. Here we have ID, residence, up to diabetes. So here there are 366 rows, that means 366 observations, and 17 columns, or 17 variables. But of these 17 variables, one is ID, which has nothing to do with our analysis, and the last variable, diabetes, is our outcome variable. So that means we are going to have around 15 covariates to be included in our models. So we can use that of this info method to determine the data types of each variable that are included in the dataset. So here ID, for example, is an int. That means it is a numeric variable. Residence, objects, age, height, they are int, sex, object, and so on. So we have here int type and floats, and that's of object type. So for this particular case, those variables with object type of data type are those qualitative variables. For example, here residence is a qualitative variable, and the values are entered as urban and rural. Therefore here it is treated as an object data type. Similarly, for sex, it is also an object data type, and the same is true for that of frame. And all the other variables are quantitative, and they are automatically numeric. So here, based on this description, those object variables, or those object type of features, are qualitative features, but those numeric type of variables are not necessarily quantitative. For example, here ID, the values are numbers, therefore it is treated as an int, but it is a qualitative variable. It should have been an object. And the same is true for the last variable, diabetes. It indicates whether the patient is diabetic or not. Therefore diabetes is just a qualitative variable, but here the type says int. That means it is numeric. Therefore here we need to identify which variables are quantitative and which variables are qualitative just by inspection, instead of relying on the data types that are listed through this info method. And in addition, if we are interested, we can get some summary statistics related to those numeric variables. So this describe method displays some summary statistics related to each variable, like count, mean, standard deviation, minimum, 25th percentile, 50th percentile, and 75th percentile, and lastly that's of the maximum. So this displays for those numeric variables. But as I said before, a numeric variable is not necessarily quantitative. So for example, here ID, the summary statistics for ID has no meaning, and the same is true for that of diabetes. The summary statistics for this diabetes variable has no meaning. Therefore, here this describe method displays summary statistics for all numeric variables, provided that all the numeric variables are not necessarily quantitative. So now let's pre-process our data, and the first step in the pre-processing of the data is to separate input features data and the target feature data. Therefore, we need to have one data frame consisting of all those covariates, and we need to have one data frame consisting of all those, let's say, target features, in case if we have two or more features. So for extracting that of the covariates data or input features data, we need to drop that of ID, because this ID variable has nothing to do with our analysis. Therefore, this ID should be removed, and the other, this diabetes variable is our target variable. It should also be removed from the input features data. So here, by calling our data frame, then we need to call the method drop. Then columns, ID column is going to be dropped, diabetes column is going to be dropped. Then this will provide our input features data frame. So this is our input features data frame, right? You would have residence, age, up to time ppn. We have 366 observations, which is the same with that of the total number of observations included in the original data set. And similarly, here we have 15 columns. That means we have 15 input features or variables. So excluding that of ID and diabetes, which were 17 variables, the total number of covariates to be considered in our classification models are 15. Therefore, we have 15 covariates to be included in our classification models. I will display this one, I don't need one. And similarly, we can extract the outcome features data. Specifically for this case, we have a single outcome variable, but in case we may have two or more outcome variables. So here diabetes, then just get the diabetes column or diabetes var only. So if I run this, now this is a pandas data frame consisting of 366 observations. The values are 0, 0, 0, 1 and so on. And if we are interested, we can look at the number of observations belonging to each category of this outcome variable. That means each category of 0 and that's of 1. So we can display using that of this value counts method, and we can add normalize to get the percentage. Otherwise, if we make like this, by default normalize is false. Therefore, there are 305 non-diabetic individuals and 61 diabetic individuals. Then if we want to look at the percentage, we can add this normalize option inside that of the value counts method. So if I run now, there are 83% of individuals which are non-diabetic and around 17% which are diabetic. Next, we are going to continue to identify quantitative and categorical covariates, because we are going to apply different types of transformation for quantitative and categorical covariates. Therefore, there is a need of identifying the quantitative covariates and the categorical covariates. So if I call our input features data and then the method info, this provides this data. Therefore, for this particular data set, those variables with an object data type are qualitative variables, and those that are not an object data type are quantitative variables. But as I said before, since a numeric variable is not necessarily quantitative in Python, we need to identify manually which variables are qualitative and which variables are quantitative. But for our case here, all those variables which are object type are qualitative, and all the other numeric variables are quantitative. So here I can just use the command select data type with type of object to identify categorical covariates, and I can use this select data type command excluding those objects to identify those quantitative features. So here we have residence, sex, and frame as categorical variables. Therefore, we have 3 categorical variables. And for the quantitative, we have age, height up to time ppn. Totally, we have 12 quantitative variables. Therefore, there are 3 categorical variables and 12 quantitative variables. Then next we have to split the input features data and target feature data into train and test sets. As we know, the train set is going to be used to train our model of interest, and the test set is going to be used to test the performance of the model trained on a certain unseen data set or data set that is not used for training. So for that case, like that of the procedures we follow in the previous videos, we are going to call the method that of the function train test split. Then we need to supply the input features data, output feature data, and the test ratio, that means test size ratio, and here just we can add this random state for ease of reproducibility. So if I run it, I can get here the shapes. There are 292 observations belonging to the train set and 74 belonging to that of the test set. And here one thing that I need to tell you is that here, for example, our outcome variable has a proportion of 83 and around 17. It is good, but sometimes there may be a problem of what we call class imbalancing. For example, either 0 or 1, if the proportion is less than something like 5%, then there is a problem of class imbalancing. In such case, when the proportion of one of the categories is very small, something like 5%, then there is a possibility of including all the cases to the train set or all the cases to the test set. Then in that case, modeling or training the machine learning models would not be possible. For now it is okay, but in case if one of the proportion of the different categories of the outcome variable is very small, we have to consider what we call stratified splits instead of what we call this completely random split. So for example, let's continue with this, and then we'll see the difference by using that of the stratified split. So for example, with this completely random split without considering stratification by the outcome variable, the proportion of zeros in the train set is about 83% and proportion of ones 70%. Similarly, in the test set, the proportion is around 85% and the proportion of ones is around 15%. So it doesn't have any problem. The proportion of just each category in both the train and the test sets are balanced. But in the case, as I said before, if the actual percentage of one of the category of the outcome is very small. In that case, instead of this completely random split, it is better to utilize what we call a stratified split. Then for that, we need to add stratify equals ydf. That means the split will be stratified based on the outcomes of the outcomes of the target variable in the based on the target variable. Therefore here just the split will consider the proportion of ones and zeros. So if I run this, and again if I check the normalized percentage of each category of the outcome variable, therefore when we use this stratify, almost exact number of proportions of each category between the train and test set will be there. Then you have 0, 83.2%, let's say, and here 0, 83.7%. And for the category 1, 16.78%, and here 16.2%. Therefore here almost the proportion of each category of the outcome variable in both the train and the test sets are almost the same. Therefore this stratification should be considered in the case where you have just a class imbalancing problem, or if the proportion of one of the category of the target variable is less than 5%, it is better to use this stratified type of split. But for now there is no need, so let's use the complete train test split, completely randomized train test split. So here the train and test sets for this, by utilizing this completely randomized train test split, the training and testing sets do not have a significantly different percentage of cases or different percentage of diabetic individuals. Now once we split the data into train and test, next we need to transform the input features data. That means all those qualitative variables should be one-hot encoded or demi-encoded, and all those quantitative variables should be either standardized or normalized. And usually if we assume those quantitative covariates have a normal distribution, standardization may be better. But if we assume that the distribution of the input covariates is not normal, we can use that sort of min-max scalar or normalization. So for now, let's consider that sort of just the standard scalar method for those quantitative variables, and we'll consider one-hot encoding for those qualitative variables. So let's instantiate our variables here. So here, for example, the first one is to use one-hot encoder. This is just a way of initialization, like that of defining a certain machine learning model. One-hot encoder, drop first. First we have to import it from sklearn preprocessing. Then one-hot encoder, drop first to consider the first category as a reference category. And for those quantitative variables, we are going to use standard scalar. Therefore this will standardize each quantitative variable to have a mean 0 and a variance of 1. And the other, instead of transforming each of either the categorical or the quantitative variable separately, it's possible to make the transformation of both categorical and quantitative variables together. And for that we can utilize this column transformer function from sklearn compose. So here let me run this one. This is one-hot encoder. This is just an initialization. So drop first the one that we have set here. Then the first category will be considered as the reference category. And similarly for the standard scalar, the parameters, let's say with mean, with STD or standard deviation. Therefore each of the quantity variable is going to be normalized with their corresponding mean and standard deviation. And instead of just normalizing normalizing the quantity variables alone and one-hot encoding the categorical variables alone, we can utilize this column transformer to do both of the transformations at the same time. So for that we need to use transform, let's say column transform. This is the name that we can specify, categorical encoder. Then use cat transform. This cat transform is nothing but this one-hot encoder, the one we have specified here. And for which features? For categorical features. Categorical features for these features. Similarly, here for the quantitative variables, we can give the name quantitative scalar. Then quant transform. What is this quant transform? The one that we defined here. Then for which variables? For those quantitative variables. For these variables. Then we can run this. Now this is again an initialization. This is an initialization of the one-hot encoder, an initialization of the standard scalar, and this is an initialization of both transformations. So here if we look at the parameters transformers, we have two types of transformers, categorical encoder and quantitative scalar, this one and this one. And specific to the one-hot encoder, you can look at, we are going to drop the first category to consider it as a reference category, and for the quantitative variables we have mean and standard deviation of each variable. And the quantitative scalar is going to be applied on these variables, the ones that we have defined here, and similarly the categorical encoding is going to be applied on these three variables, residence, sex, and frame. Now this is yet an initialization. The transformation is not done yet. Therefore, we are going to call this function and use fit transform and pass the training data to make the transformation on the training set. So we need to call the method fit transform. Now this fit transform has two functions. One, it gets the summary quantities from the trained data set. Summary quantities, that means here, for example, for those quantity variables, the fit method will get the mean and standard deviation of each quantitative variable. And the transform method applies these parameters to transform those quantitative variables. So the same is true for the qualitative variables. So we need to call this fit transform method on the training set. Then now the transformation is done on the training set. The transformation is done on the training set. Here, for example, let me go back once. Here in the input features, we have 15 input features. We have 15 input features. But let's check the variable names or the total number of variables in the transformer dataset. From here, for example, we can call this transform, then dot get, let's say, feature names out. This one, and instead of this, let me count the number of variable names here. 16. In the original dataset, we have only 15 covariates. Only 15 covariates. But in the transformation, it becomes 16. Why it is 16? Because we have some of the qualitative variables having categories 3 or more, specifically if we consider that of the frame variable. Let me call this variable and the frame variable frame. And here if I apply value count, Okay, x frame x, oh sorry, f should be capital. Yeah, therefore here this frame variable has three categories: medium, small, and large. Therefore when we use one-hot encoding, dropping one of the category as a reference, therefore this frame variable is going to be represented by two dummy variables. Those two dummy variables are here frame medium and frame small. The reference category is that's of frame large. Therefore that's why the number of transformed features becomes 16, which is larger than the actual number of input covariates, which is actually 15. Therefore here we have categorical encoder. This is nothing but this one, categorical encoder, then underscore residence urban, then the reference category is rural, and for sex the reference category is female, and for the variable frame the reference category is large. Here we have frame medium and frame small, and the others are quantitative variables: quantitative scalar age, quantitative scalar height, and so on. Therefore here our model is going to have, let's say if we utilize a certain standard linear model, the number of parameter estimates will be 16, because here we have 16 transformed input features instead of the actual number of covariates that are included in the original dataset. So now the transformation in the train dataset is done. Next we need to apply the learned information or learned parameters or learned transformation on the test set. And here let me consider once again transform, I think, okay, here what I need to tell you is that here we can say transform dot named transformers underscore, and then we need to supply the, I think, this quantitative scalar. I think this should be in double quotes or single quotes. So let me check. Named transformers. Okay, yeah. Okay, yeah. So let's assign here standardizer. Let's utilize this, and yes, here's our standardizer. From here we can extract that's of the mean and standard deviation. Standardizer dot mean, this is the mean of all the quantitative variables. Mean of the first is that's of age, and the second, and so on. Similarly we can use for the standard deviation, we need to say scale. Now these values are already computed from the training dataset. Then these values are going to be utilized to transform the test dataset. Then for example, age in the test dataset is going to be transformed using a mean of 47.13 and standard deviation of 16.44, and the same is true for the others. Therefore in the test set we need to call the method transform. Then this will apply those summary quantities that are stored in the transformer and apply for the test dataset. Therefore always we have to use fit transform for the training set, and this transformation should be done first, and next we have to call the method transform and pass that of the testing dataset. Then I can run this. Now the test dataset is also transformed. It's also transformed. So if we are interested, we can examine the shape of the train and test sets and just to ensure that the actual number of observations and encoded covariates are the same or not. So the train shape is 292 by 16 and 74 by 16. So 292, yeah, 292, 17. But the original dataset has 15 variables, but due to the categorical covariates having categories more than 2, the number of encoded covariates becomes 16. Now let's just convert the outcome data into NumPy array. Here this is nothing but just we are transforming, and we are not transforming, we are just converting the data type. Originally, for example, YDF, this is Y-trained-F, it is a pandas series format, but Y-train is a NumPy array format, Therefore here we are not doing any transformation on the outcome dataset. Rather we are just converting the data format from pandas series format to a NumPy array format. Therefore this is not a transformation. The transformations should be applied only on the input features data. Now we are in a position to train several candidate models because we have already transformed and pre-processed our data and converted the data in the way that the machine learning algorithm requires. So we are going to train several models: logistic regression, including ridge logistic regression, lasso logistic regression, elastic net logistic regression. All of these are going to come from the logistic regression class from the sklearn linear model module. So we are going to change some of the penalty parameters to be L2 and to obtain ridge logistic regression, and L1 for that of lasso logistic regression, and for that of elastic net we need to specify that's of the regularization parameter and that's of the L1 ratio. There is also another type of classifier that is applicable for classification problems called ridge classifier. This ridge classifier is like that of let's say a linear regression which treats the outcome variable as having values 1 and 1, or for more detail here let me just call once RIDG ridge classifier. Let me instantiate here. I think I have to import first from sklearn dots what you call linear model import this ridge classifier. Then let me instantiate here, just instantiated. Let's go to the documentation. So what this model do is, this classifier first converts the target values. Our target values are actually 0 and 1. Then they are converted into -1 and 1. Then treats the problem as a regression model. In the case of multi-class classification model, it will treat as a multi-output regression, but in the case of a binary classification model, just the model will treat the problem as a regression model by converting the target values 0 and 1 into -1 and 1. So this ridge classifier is also a classification model, and we have support vector classifier, k-nearest neighbors classifier, and all the other methods just having the name classifier, as we have seen in the previous video using the term regressor. So we are going to fit all these 15 models and then select the one that performs best. So we can import them just here. They are going to import each of these models are going to be imported from their corresponding modules. So this lines of course imports all the 15 models described here. So let me run. Now all the necessary classes for fitting these 15 models are imported. Now, as we have seen in the previous video regarding that of regression models, instead of just tuning each models first, it is better to first train the models with their default values and then compare. And then after comparing, we may select one of the model as best, and that model can be further trained to have just the best performance of that model. Otherwise, just tuning each model is somewhat exhaustive. So for this case, I here presented all the model instantiations and give their names here in a dictionary format. This is just a dictionary format, giving the name of the models and their corresponding instantiations. So for example, for logistic regression, we need to instantiate logistic regression, and then we have to set the penalty to none. Because as we saw again in the previous videos, logistic regression by default in scikit-learn is a rich type of regression model. Therefore, we have to set penalty to none to get the standard logistic regression model. Then if we do not consider this one, the model will be this one. That means it is a rich logistic regression model. And for the lasso logistic regression model, we have to change the penalty to L1, and some of here this L1 works on a specific number of solvers. Therefore, the solver should be also changed to liblinear, because liblinear is one of the solvers that L1 penalty works. And similarly, in the case of ElasticNet, we need to change the solver to Saga, because for ElasticNet penalty, Saga is the only applicable solver, and we can specify the L1 ratio. And for ridge classifier, SVC, and so on. Therefore, this is just the presentation of the names of the models together with their instantiation in a dictionary format. So for example, how many models do we have here? I have to run this first. We have 15 models. This is the name of the names. These are the names of the models, and these are their corresponding instantiations. Then for a binary classification model, there are some common evaluation metrics like accuracy, precision, recall, F1 score. We need to have a model to have higher values in each of these metrics. So we can import this accuracy score, precision score, recall score, and F1 score to obtain these scores from a scikit-learn matrix. So here I defined all of these evaluation metrics into this function to return the accuracy, precision, recall, and F1. So again, let me run this, because instead of calculating the accuracy score for each model and for each dataset for train and also for test, it's better to define the function in this form, and later on we can just call our function here instead of repeating every time accuracy score, precision score, recall score, F1 score. So now let's go to that of the main training function. Now this is a training function. Here again, we are not going to train each model separately. Rather, it is better to write a function, something like this, and then run the training or train the models using just this single function all in one. So here we need to supply for this function, we need to supply the models. These models are nothing but the ones that we have defined here as binary model select. We defined all the models here. And we need to supply the train and test data. Then here we initialize the model scores to get the accuracy, precision, recall, and F1 score for the training and testing sets of each model. Then for each model we are going to train our model and then get the predicted value of the train and get the predicted value of the test dataset. and based on these predicted values of train and test sets, we need to obtain this accuracy, precision, recall, F1 scores. So these training scores are going to be saved here, and these testing scores are going to be saved here. Then finally, this scores or this model scores dictionary is going to be converted into a pandas data frame. Then finally, the function returns the model scores data frame. So I can run this function. Therefore, there is no need of training each model or each of these 15 models separately. Rather, we just need to call this function train classification models. Here I called here, then the models dictionary, then the dataset. Then I can run this. Then this automatically displays the summary measures of all the models in one, including the training sets, testing sets. So starting from logistic regression, ridge logistic regression, lasso, elastic net, ridge classifier, support vector classifier, up to adaptive boosting classifier, the results are displayed here. Train accuracy, train precision, train recall, train F1 score, test accuracy, test precision, test recall, and test F1 score. So here let's focus on the accuracy metrics, train accuracy and only test accuracy. And first, for better visualization, let's sort this data frame by the test accuracy. So this code sorts this scores data frame based on test accuracy. So now here this data frame or the scores data frame is sorted by test accuracy. The largest accuracy is 0.986. This corresponds to that of CBC, categorical boosting classifier. The train accuracy is 100%. Therefore, this is the best model. Usually, to identify a certain model as best, it is better to have a difference less than 2% between the train accuracy and the test accuracy. So here we have 1, here we have 0.98, therefore the difference is almost less than 2%. Therefore, here we can say that this CBC model is neither overfitting nor underfitting. Therefore, this CBC, categorical boosting classifier, is better of all the other models. But if we consider here lasso logistic regression, the train accuracy is 90% and the test accuracy is 95%. Therefore, here the train accuracy is lower. That means lasso logistic regression is now a little bit underfitting. It is a little bit underfitting. And the same is true for that of here. This logistic regression model, 89%, the test accuracy 95%. So therefore the train accuracy is lower, far from that of the test accuracy. Again, this logistic regression has also a problem of underfitting. And the same applies for that of ridge classifier. Now let's come to here, XGB, the extreme gradient boosting classifier. The train accuracy is 100%, but the test accuracy is 95%. Therefore, the test accuracy is far from the train accuracy. Here we can say this extreme gradient boosting has a problem of overfitting. And the same is true for that of this random forest classifier. It has a better training accuracy, but the test accuracy is lower. Therefore, again, this random forest classifier has the problem of overfitting. And the same is true for that of, for example, here again, extra trees classifier, decision tree classifier, and here gradient boosting classifier. They have a problem of overfitting. Therefore, of these 15 candidate models, CBC or the categorical boosting classifier is the best model. It is the best model. Therefore, we have to consider this one for further analysis. Maybe for further fine-tuning of the hyperparameters, or maybe for identifying the relative importance of the covariates, and so on. So now let's consider what we call feature importance, or identifying the relative contribution of the different factors included in our models. So feature importance measures how much each feature contributes in reducing the model's error or in improving the model's predictive power or predictive performance. So the higher the value is, the better the feature has an importance in predicting the outcome of interest. So for feature importance in linear models, we are going to consider just the attribute COEF underscore. Just looking at the coefficients of the linear model is sufficient to identify the feature importance. So for linear models here, for example, logistic regression, whether it is ridge, lasso, or elastic net, they are linear models. Ridge classifier is also another linear model. So for such models, we need to call the attribute COF and look the values. And here for these linear models, we are going to consider the magnitude of the effect. That means the magnitude, the absolute value of the magnitude. Whether it is positive or negative, it doesn't matter. But the one having a larger absolute value indicates that the variable is more important because it reflects the strength of the effect. So let's illustrate for logistic regression model. Note that here our best model is this categorical boosting classifier. So we need to identify feature importance using this model. But to see how the feature importance is identified in linear models, let's consider a logistic regression model. Here we have instantiated the model, and here this is the code for training the model. So let me run. Now the model is trained, it's fitted. So I need to call this method COF, right, on this trained model. Therefore the one having a larger value is the most important variable. So for example, maybe this variable, the variable corresponding to this value, maybe here this one is having a larger value, yeah, but we don't know to which feature name this value corresponds. So we can get the feature names from the transformer. So let's get the feature names. So the first value corresponds to this one, residence urban. Second one, sex male. Third one, frame medium, and so on. But let's convert these two objects into a data frame so that we are able to compare that's of this feature importance. So we can use this 4-line codes to convert them into a data frame. So here I sorted these values by this importance variable. So therefore here the one having the largest contribution is stabilized glucose, and the second cholesterol level, third age, and fourth HDL. Now look, HDL, it is negative. Even if it is negative, the effect, we are interested on the effect, therefore the effect is large. Therefore HDL is the fourth important variable in explaining diabetes based on our this logistic regression model or this linear model. So for linear models we need to call just this COF attribute. Second, for tree-based models there is an attribute called feature importance. These tree-based models are decision tree classifier, random forest classifier, gradient boosting classifier, extra trees classifier, AdaBoost classifier, extreme gradient boosting classifier, and categorical boosting classifier. So in this case the feature importance is usually based on splits because these are tree-based models. Therefore the feature importance is calculated using splits, specifically using that of a method called Gini importance, gain, or permutation importance. So the feature importance are actually non-negative, and they measure the contribution in reducing that of the model error how much just the model, that's how much the error will reduce just for each of the variable included in the model. So here we have already selected as our best model this CBC model, that is a categorical boosting classifier. So let's examine the feature importance for this variable. So cat boost classifier, I instantiate here and train here, and then we can call the feature importances attribute. That is it. Therefore, if I run it, therefore these are the feature importance. As before, we don't know to which value this value correspond. So it's better to convert them into a certain data frame format, right? That's the better way. So I can convert into data frame, and I sorted based on their relative importance. So again, stabilized glucose is 31. It is the largest of all. Age, cholesterol, SBP. Therefore, these are the most important factors in explaining, let's say, the probability of diabetes. But here, residence, sex, and frame of category small compared to the large category, they have just the smallest importance in reducing the model's predictive error. So stabilized glucose and age are the most important features. We can say sex and this frame small compared to frame large have the smallest importance. So for these tree-based models, we just need to call only this feature importance underscore. Now lastly, there are also some models without direct feature importance. So for that, we are going to consider what we call permutation importance. And actually, this method is model agnostic, or it can be applied for any kind of model. It is independent of the model type. So if the feature importance here is negative, it means the model does worse when the feature is shuffled. Therefore, that means that feature is not important. And if the feature is actually important, in that case the feature importance is going to be positive. Therefore, negative permutation importance implies the feature likely adds noise rather than the signal to the model. Therefore, such models, or not such models, input features with negative permutation importance are just lots of unimportant factors which add noise rather than the signal to the model. And then it's also better to evaluate on the test and validation set. Therefore, here, for example, in the linear models, the coefficient may be negative or positive, but regardless of whether it is positive or negative, we are interested on the magnitude. Therefore, if a variable has a large negative value, that variable is an important variable because it has a significant effect. And for that of the tree-based models, here the values will be positive. It's okay. The one having a larger value is the most important feature or variable. But in the case of permutation importance, if the variable has a negative value, that variable is an important variable. Even that variable is adding noise to the model, even instead of that of a signal. Therefore, here we are not going to consider the absolute value of the feature importance. Rather, we are going to consider the actual value of the feature importance. So if a feature has a positive value, that feature is very important. If a feature has a value of 0, that feature has no contribution or no importance. But if a feature has a negative value, that feature has a drawback, or that feature adds unnecessary noise. Therefore, here for models without direct feature importance, we can consider support vector classifier, k-neighbors classifier, and bugging classifier. These do not have the co-of attribute or the feature importance attribute. So let's consider using this support vector classifier just to see how this permutation importance works. We have to instantiate the support vector classifier and fit our model. Now we fit our support vector classifier. So here, for example, if I try svc dot coef underscore, it says coef is only available when used a linear kernel, right? Here by default support vector classifier is a linear model, and it uses the radial basis kernel function. Therefore, it doesn't have coefficients to be interpreted associated with each input feature. Similarly, if we consider what called importance feature, right? Feature importance, feature importance. Again, SVC object has no attribute feature importance. Therefore, in such case, we have to utilize the permutation importance. So for this purpose, we need to import permutation importance from sklearn inspection. Then let's consider the train set. We have to supply the estimator, that is SVC, and supply that of the train set. Let the number of repeats be 10. As the number of repeats is larger, it is better, but computationally it will be expensive. And finally, we need to call the method just that of the attribute importance mean. So let me run. These are the importance. As usual, let's consider that of the data frame. Now for this case, all the values are positive. So the one having a larger values stabilize glucose, and this ratio variable heap cholesterol. These are most important variables based on the support vector classifier. Let's consider the test set. It is better to utilize also the test set and compare which features are contributing to the performance in the training set and the performance in the test set. So here I changed the dataset to test. These are the features based on the test sets, and let me see that of the data frame. This is the data frame. So stabilized glucose and age are contributing in improving the model's performance for based on the test set. But here we have some negative values, right? Therefore, this means these variables are contributing noise to the model utilizing this test set. Therefore, these variables are unimportant variables. They are completely unimportant variables. But the one having here the values 0 have no contribution. They have no contribution at all. They have no contribution, but these features having negative values are contributing a noise to the model. That means, therefore, these features are not completely important. So stabilized glucose here is the one having the largest value. It is the most important variable. And here if we consider systolic blood pressure, frame, and these variables over here, not only this one, but systolic blood pressure, let's say ratio, HDL, we have sex, not frame and ratio here based on this set, height and hip circumference. These are variables contributing in a negative way, or variables contributing a noise instead of a signal to the model. So these variables have negative contribution. The remaining, not only the remaining, but there are also other variables. Let me list from weight to let's say here way to last heap have negative contributions and the remaining factors have no contribution, but these variables are having a negative contribution. So this is the way how we can identify feature importance in the linear models. We need to consider the attributes of. In the tree-based models, we need to consider the attribute feature importance, but for those models without direct feature importance attribute, we need to use permutation importance. So this is all about today's video. Thank you for watching.